Good afternoon, everyone. We are the working unit number 2, and we will discuss today about the topic diesel engine. And that's how a diesel engine sounds like. And working unit number 2 proudly presents its members. In the left corner, we have the most beautiful member of the group. She is Roslyn Segunla. In the right corner, she is the TikTokerist of the group. We have LJ Haiba. In the left corner, we have the escort of the group. He is John Mark Manayaga. And in the right corner, we have the undefeated champion of the world, Ryuji Ensura. And yours truly, John Lester Pulinas.
Good afternoon, everyone. Let's start with what is a diesel engine. A diesel engine is a type of internal combustion engine that uses compression ignition to burn fuel, rather than spark ignition like gasoline engines, unlike gasoline engines that rely on spark ignition. Diesel engines compress the air in the cylinders, which causes the fuel to ignite and produce power. The diesel engine was invented by German engineer Rudolf Diesel in the late 19th century. Diesel began working on the engine in 1890s with the goal of creating a more efficient and powerful alternative to the steam engine, which was the primary source of power for industrial machineries at the same time. The first prototype diesel engine was built in 1892 and underwent several improvements before being patented in 1898. The diesel engine was a significant breakthrough in engine technology, as it was able to use a more efficient fuel source than steam engines and gasoline engines, which were the primary engines in use at the time. Let's now take a look at the importance of the diesel engine in the industry. Diesel engines are widely used in transportation, agriculture, and construction, and other industrial due to their durability, fuel efficiency, and high torque output. Diesel engines are vital in industries due to their high power output and torque, making them suitable for heavy-duty applications such as industrial machineries and large vehicles. Their fuel efficiency is a key advantage, providing cost saving in fuel consumption in industries with extensive transportation needs. Additionally, diesel engines have a long lifespan and require less maintenance compared to the gasoline engines, contributing to their importance in industrial settings. As we all know, thermodynamics is a study of relationships between heat, work, and energy. It plays a role in design and operation of the diesel engines by providing a framework for analyzing the thermodynamic processes that occur during engine operation. This includes the diesel cycle, which describes the sequence of events that occur during a diesel engine's combustion, as well as the laws of thermodynamics that govern energy transfer and conversion.
Let's now look at the parts of a diesel engine. These are the parts of a diesel engine. First, the cylinder and the cylinder head. Piston and piston rings. Connecting rod. Crankshaft and crank webs. Main bearing. Crank in and bearing. Nozzle. piston ping and bearing, exhaust valve, cam part, valve springs, cylinder block or crankcase, flywheel, bed plate, and also a diesel engine has a cooling water jackets.
Let's now go to the diesel cycle, which is the sequence of events during diesel engine combustion process. And these are the 4-stroke the diesel engine undergoes. First, we have the intake stroke or suction stroke. During this stroke, the piston moves downward, creating a vacuum that allows the air to enter the combustion chamber through the open intake valve. Second is the compression stroke, and in this stroke, the piston moves back upward, compressing the air to a high pressure and temperature. The diesel fuel is then injected into the combustion chamber, where it is atomized and mixed with the hot compressed air. And the third one is the power stroke. And during the stroke, the fuel-air mixture ignites, creating a rapid expansion of gases that forces the piston downward. This produces the power that drives the engine. And the fourth and last stroke is what we call exhaust stroke. And in this final stroke, the piston moves back upward, pushing the exhaust gases out of the combustion chamber through the open exhaust valve. The cycle then repeats with the intake valve opening again to begin another cycle. To understand further the 4 strokes that diesel engine undergoes, let's watch this video.
An internal combustion engine transforms the chemical energy in fuel to mechanical energy. Diesel engines, which have been serving mankind for over a century, are the most versatile and economical IC engines. To release the chemical energy in diesel effectively, an atomized form of the fuel is made to contact with high temperature and high pressure air. This energy is effectively transferred as mechanical rotational energy. So the operation of a diesel engine is all about producing high temperature and high pressure air continuously. We will see how this is achieved in this video. Piston, connecting rod, crank, and cylinder form a mechanism called slider crank mechanism. Here, the linear motion of the piston is transformed to a rotary motion at the crank. In an IC engine, this mechanism is properly supported in an engine block. Cylinder head, valves, and fuel injector are fitted above the engine block. When the piston moves downwards, inlet valves open and fresh air from outside is sucked in, or, in other words, the engine breathes. During the return stroke, inlet and exhaust valves are closed, and the air inside the cylinder gets compressed. During the compression stroke, the piston does work on the air, so the temperature and pressure of the air will rise to a level which is higher than the self-ignition value of the diesel. An atomized form of diesel is injected into this compressed air. The fuel gets evaporated and undergoes an uncontrolled spontaneous explosion. As a result, the pressure and temperature rise to high-level values. The high-energy fluid pushes the piston downwards. The hot air does work on the piston, and energy in the fluid is converted to the mechanical energy of the piston. This is the only stroke where the piston absorbs power from the fluid. Due to inertia of the system, the piston moves upwards again. This time, the exhaust valves open and the exhaust is rejected. Again, the suction stroke happens. This cycle, which has a total 4 strokes, is repeated over and over for continuous power production. You may have noticed that a bowl is provided on top of the diesel engine piston. During the compression stroke, this bowl helps produce air that is rapidly swirling. Thus, the injected fuel gets mixed with the air effectively. The mechanical design of IC engines, particularly that of diesel engines, is a challenging and interesting task. Since the combustion process in diesel engines is never uniform and smooth, they are prone to more vibration and noise compared to petrol engines. Thus, diesel engines require a rugged structural design. Out of the 4 strokes, it is only during the power stroke that a tremendous amount of force is exerted on the piston. So a single-cylinder engine will always have high force non-uniformity as shown. Similarly, the output power will also have a fluctuating nature. But with more number of cylinders, one can overcome these problems. Consider this 4-cylinder engine. Here, 4 different strokes can occur at a time. So the power stroke is always present in the engine. As a result, a 4-cylinder engine will have better force and power uniformity. In short, the more cylinders an engine has, the smoother it will operate. A 4-cylinder engine generally operates on the following firing order. A heavy flywheel which acts like a power reservoir further helps in smoothing out non-uniformity of power. A huge unbalanced force arises in the form of dynamic unbalance due to the excessive mass at the connecting rod side. This is negated by providing counterweights on the crank side. Opening and closing of valves are accurately controlled by a pair of camshafts. Camshafts derive motion from the engine. It is clear that the camshafts need to rotate at half the speed of crankshaft. We hope you had a nice introduction on the working of diesel engines. Thank you.
Let's now move forward to the 4 processes in the diesel engine. First, the isentropic compression. In the cycle, it is a constant entropy compression process. It is observed in the process 1 to 2. It is an adiabatic compression process in which the piston compresses the air-fuel mixture inside the cylinder from pressure P1 to P2. Second is we have the isobaric heat addition. The constant pressure heat addition process is also known as the isobaric process, and it is observed in the process 2 to 3. It is a constant volume heat addition process, and in this process, a spark plug produces a spark to ignite the fresh charged air plus fuel, which causes the pressure inside the combustion chamber to raise from P2 to P3. Third is we have the isentropic expansion. In the diesel cycle, it is the constant entropy expansion process, observed in the process 3 to 4. It is an adiabatic expansion in which the high-pressure gases expand inside the cylinder from P3 to P4. And the last process is we have the isochoric heat rejection. The last process in the cycle is the constant volume heat rejection process, also known as the isochoric process, which is observed in the process 4 to 1. It is a constant volume heat rejection during which the heat is rejected outside of the cylinder.
A typical diesel automotive engine operates at around 30% to 35% of thermal efficiency. Low-speed diesel engines, as used in ships, can have a thermal efficiency that exceeds 50%. This is the formula of finding the thermal efficiency of diesel engine, where efficiency of diesel is the maximum thermal efficiency of a diesel cycle. The alpha symbol is the cut-off ratio V3 over V2, which is the ratio of volumes at the end and start of the combustion phase. CR, which stands for the compression ratio, and K is equals to Cp over Cv is equals to 1.4, which refer to the specific heat capacities at constant pressure and constant volume, respectively. The first law of thermodynamics, also known as the law of conservation of energy, says that energy cannot be created or destroyed, only change from one form to another. Diesel engines convert the chemical energy in diesel fuel into mechanical energy to power vehicles and machines. In diesel engines, the first law of thermodynamics can be seen in different ways. For example, the fuel's energy is turned into heat energy during combustion, which raises the pressure and temperature in the engine cylinder. This pressure and temperature push the piston to move and turn the heat energy into mechanical energy for work. The first law of thermodynamics can also affect the efficiency of diesel engines. Efficiency is measured by the ratio of work output to energy input. For diesel engines, the energy input is the fuel's chemical energy, while the work output is the mechanical energy used for tasks. The engine's efficiency depends on the factors like combustion, compression ratio, and design.
The second law of thermodynamics is a fundamental law of nature that governs the behavior of energy in all physical systems. It states that the total entropy of a closed system will always tend to increase over time, unless there is external force that acts on the system to prevent this from happening. The second law has important implication for engine performance, as engines are essentially devices that convert energy from one form to another. In particular, the second law sets limits on the maximum efficiency that any heat engine, such as diesel engine, can achieve, as well as the amount of entropy that is generated during the engine's operation. The diesel engine's entropy generation is a significant factor that can affect engine performance. This is about the combustion process that takes place in the engine produce a large amount of heat energy, which can lead to creation of high level of entropy. To minimize the impact of entropy generation, engine designers can use various strategies such as improving the fuel injection system, optimizing the air-fuel ratio, and using advanced materials and coating to reduce heat losses.
To calculate engine efficiency using the second law, it is necessary to consider both the amount of heat energy that is input into the engine, which is the Qin, and the amount of work energy that is output by the engine. The efficiency of the engine is then given by this equation. Please take a look at this equation. In this equation, it expresses the fact that some of the energy input into the engine is lost as waste heat due to the second law's requirement that entropy must increase. The efficiency of the engine is therefore always less than 100%.
Finally, The concepts of availability and energy efficiency are also important in the context of engine performance. Availability is a measure of the maximum amount of work that can be extracted from a given energy source, while energy efficiency is a measure of how efficiently this work can be extracted. Both of these concepts are closely related to the second law of thermodynamics, and they can be used to analyze and optimize engine performance in a variety of ways.
Diesel combustion is the process of burning diesel fuel in a diesel engine to produce energy in the form of heat. Diesel combustion is characterized by its high compression ratios, which results in high temperatures and pressures within the engine cylinder. This high pressure and temperature cause the fuel to ignite and burn, releasing energy that drives the engine.
The emissions produced by diesel engines are a result of the combustion process. The thermodynamics of diesel engine emissions refer to the study of how these emissions are produced and how they can be controlled. Diesel engine emissions include particulate matter or PM, nitrogen oxides, carbon monoxides, and hydrocarbons. Combustions and thermodynamics models can be used to predict the emissions produced by diesel engines. These models typically take into account factors such as fuel properties, engine designs, and operating conditions. By using these models, it is possible to optimize engine performance and reduce emissions.
Let's now look at the differences of diesel engine from gasoline engine. These are the differences of diesel and gasoline engines. First, the fuel type. Diesel engines use diesel fuel, which is less volatile than gasoline and is more suited to compression ignition. Second, the ignition system. Diesel engines rely on high compression and heat to ignite the fuel, unlike gasoline engines that use spark plugs. Efficiency. Diesel engines are generally more efficient than gasoline engines due to their higher compression ratios and the fact that diesel engines has a higher energy density. Another one is torque. Diesel engines produce more torque than gasoline engines, making them better suited for heavy-duty applications. Also, its emissions. Diesel engines tend to produce more particulate matter and nitrogen oxides emissions than gasoline engines, leading to increasing regulation and the development of emission control technologies. Overall, diesel engines are more efficient and produce more torque than gasoline engines. But they also have changes related to emissions control.
Okay, so those are the things that we should take note about diesel engines. So, let's now proceed to the conclusion. So we conclude that diesel engines are popular in different industries due to their strength, fuel efficiency, and high torque output. Understanding the thermodynamic processes during diesel engine operation is crucial. Also, I just want to add that in this lesson we have learned the relationship of the first law of thermodynamics with diesel engines, that they convert chemical energy in diesel fuel to mechanical energy to power vehicles and machines. Its efficiency depends on various factors, including combustion, compression ratio, and design. Also, we have learned the application of the second law of thermodynamics in diesel engine combustion, which produces a lot of heat energy, which can cause high levels of entropy. Strategies such as improving the fuel injection system, optimizing the air-fuel ratio, and using advanced materials can minimize the impact of entropy. So future research on thermodynamics in diesel engines will primarily focus on improving efficiency and reducing emissions. This includes developing advanced combustion strategies, optimizing fuel injection and combustion processes, and improving engine materials and coatings to reduce heat losses. There will also be more emphasis on developing alternative fuel sources and reducing the environmental impact of our diesel engines. And that's all for the topic of diesel engines. Thank you very much, and I hope that you have learned a lot of things in this topic.
Ha ha ha!